Today we're going to review the first three sections in Chapter 6, which were 6.1 to 6.3. So remember, we can have one of three things happen when we have a solution to a system of equations. We could have intersecting lines that provides exactly one solution. We could have parallel lines or no solutions where the lines will never intersect. Or we could be talking about the same line with infinitely many solutions. So section 6.1, we did solve by graphing. So let's refresh our memory and practice that. The first equation I'll do in red. We want to graph y equals 2x plus 1. Remember, we start at the y-intercept, so that's up at 1, positive 1 on the y-axis. And our slope is positive 2, or 2 over 1. So I'm going to go up 2 and to the right 1. That will give me a slope, a line with positive slope. I'm also going to go down and to the left. Remember, initially I'm not sure where these lines are going to intersect, so I like to go all the way across the graph. That way I don't have to extend the line later. The second equation I'll do in blue, and that's 3x minus 1. So we're starting at negative 1 on the y-axis, and my slope is a positive 3 over 1. So I'm going up 3 and over 1. I'm also going to go down 3 and over 1. Even though I can see where the line already intersects, I like to extend my line all the way across the graph. And then remember, your answer is an ordered pair where the two lines intersect, and we need to name that ordered pair. It is 2, 5. Example 2 is solved by substitution. This was section 6.2, where we want to solve one of the equations for a variable, and then we want to plug that in to the second equation for that variable. Now you can see in number 2 we have y equals negative x plus 2. We already have the first equation solved for y. So I'm plugging all of this in to the second equation. The question is, where does it go? Hopefully you're saying it goes in for y, because that's what it equals. So I'm going to rewrite the second equation, substituting in the negative x plus 2 for y. And now I have an equation with one variable. 3 times a negative x is minus 3x, or negative 3x. You'll see here 3x minus 3x, those cancel, and I'm left with 6 equals 12. So this is one of our special cases. We don't see it as often, but when the variable eliminates, we need to look at what we're left with. 6 does not equal 12. Therefore, this is false. And we're talking about parallel lines. Parallel lines never intersect, so we say no solution. Example 3, we want to solve by elimination. Remember, in elimination, we need the coefficient on the variable to be the same, but opposite in sign. So I have 2x and 3x. I also have 3y and 1y. It's a little easier on this one to multiply the bottom equation by a negative 3, because that will make my y's eliminate. If I wanted to eliminate x, I would have to multiply the top equation and the bottom equation. So I'm going to rewrite the first equation, 2x plus 3y equals 8. I'm going to multiply every term in the bottom by negative 3. And now I'm going to add the equations. 2x minus 9x is negative 7x. The positive 3y and negative 3y eliminate, and I have negative 7. Divide both sides by negative 7. And we get that x equals 1. And now I want to plug that 1 back into either the first or the second equation so that I can solve for y. It's a little bit easier to use the second equation since there's no coefficient on the y. So we have 3x plus, this is where I'm substituting in the 1 or plugging back in the 1. 3x plus 1 equals 5. And I've actually plugged that in the wrong place, sorry. I want to plug it in for the x because I'm solving for y. So 3 times 1 is 3, plus y equals 5. Subtract 3 from both sides, and we get that y equals 2. So our answer, where the two lines intersect, is 1, 2. So we were able to review solving by graphing with an example, solving by substitution with an example, and solving by elimination with an example. We'll work on a review worksheet in class.